everyone. Today I'll be talking about fluorouracil or 5-FU, a key keto- chemotherapy drug used to treat cancer like colon, breast, and digestive tract cancers. This presentation will cover how 5-FU is metabolized, how it inhibits RNA synthesis, and the mechanism behind the effectiveness in the cancer treatment. 5-FU was first developed in the 1950s after scientists observed that cancer cells utilize uracil more rapidly than normal tissue. This discovery led to the development of fluoropyrimidine, including 5-FIU. Over the years, combining 5-FIU with newer chemotherapies have significantly improved response rates from advanced colorectal cancer by as much as 40% to 50%. So, how does 5-FIU works? Once it enters a cell, it is metabolized into three active compounds: FDUMP, FDUTP, and FUTP. These compounds disrupt the process cancer cells rely on for survival, namely DNA and RNA synthesis. Let's start with how 5-FU is metabolized. After being taken up by the cell, 5-FU is converted into an active metabolite through enzymatic reactions. These metabolites are critical for its anti-cancer effects. The first key metabolite is FDUMP. FDUMP plays a central role in inhibiting DNA synthesis. The second, FUTP, is incorporated into RNA, disrupting RNA synthesis. Finally, FDUTP gets misincorporated into DNA, causing damage and instability. This process involves enzymes like thymine phosphorylase, which help convert 5-FIU into an active form. By targeting multiple pathways, 5-FU can effectively stop cancer cells from growing and dividing. Now, let's focus on how 5-FIU affects RNA synthesis. One of its metabolites, FUTP, competes with uridine triphosphate or UTP during RNA synthesis. Normally, UTP is incorporated into RNA to help build functional strands. But when FUTP is used instead, it creates a faulty RNA. This disrupts normal RNA processing and function, ultimately impairing proteins products. For cancer cells, which are highly dependent on rapid protein synthesis, is significantly a blow. Next, let's look at how 5-FIU interferes with DNA synthesis. The key player where is FDUMP, which binds tightly to an enzyme called thymosidine synthase, or TS. TS is responsible for converting DUMP into DTMP, a precursor for thymine nucleotide, which are essential for DNA replication. When FDUMP binds to TS, it forms a stable complex that prevents the enzyme from functioning. Without DETMP, the cell cannot synthesize DNA properly. This effect is particularly harmful to cancer cells, which rely heavily on DNA replication for their rapid division. To summarize, 5-FU is a powerful chemotherapy drug because it targets two critical processes in cancer cells: DNA and RNA synthesis. It metabolizes FDUMP, FUTP, and FDUTP, works together to inhibit thymidine synthesis, disrupt RNA processing, and damage DNA. By blocking these pathways, 5-FU significantly limits cancer cells to grow and survive. This makes a cornerstone of modern chemotherapy regimens, specifically for colorectal and other sensitive cancers. In closing, FU has been a game changer in oncology for decades, and it's able to disrupt multiple pathways in cancer cells, um, underscores its importance. Thank you for your attention.